Let's talk about momentum. Chapter 10. So we're going to do momentum, talk about the really nice parts of momentum, some of the ugly parts with momentum, and then we'll bring energy back into it. Newton's third law, I know that the force on A from B is equal to the negative of the force on B from A. Negative just being a directional thing. Force that B exerts on A, just emphasize that, it's the force B exerts on A is equal in magnitude, opposite direction to the force that A exerts on B, Newton's third law. We know that two objects that interact with each other will interact with each other for the same amount of time. Times time. And, well, actually, you know, with most of the groups, I don't do the calculus-based version of it, so that's what that is. So F AB dt equals negative F dA dt. Integrate both sides. And Newton's second law, what is force equal to?
Mass times acceleration.
So this would be the mass of A times the acceleration of A dt. Is the negative mass of B times the acceleration of B dt from some time initial to time final. They're in the same direction. I guess technically the accelerations are still vectors. Assuming for right now that the mass is not going to change, the mass of an object doesn't change as we go, I can bring that out. So mass of A times the integral from some initial time to some final time of A dt is the negative mass of B times the integral T final acceleration of B dt. And what is the integral of A dt?
Velocity.
So we have the mass of A times the velocity as a function of time from some time initial to time final is equal to the negative mass of B times V, velocity with respect to time, some time initial to time final. So we end up with MA V final, V final minus MA V initial is negative MD V final plus MB V initial. And now let's get the finals and the initials together. I'll bring this over to the left side, this over to the right side, and so I have MA V final. This is for A, B, and B. Plus MB, VB final is equal to MA, VA initial plus MD, VB initial. All right. At this point, physicists get tired of writing. But this MV, whatever this MV is, if I add up the total initial value and the total final value, I should get the same thing. In other words, it's a conservation law. My total initial equals my total final. In physics, we call that conservation. This P times, mass times velocity is usually symbolized by the letter P, which is momentum. Now, I've seen some physicists try to give some better explanation, feeling like momentum is this fundamental property of nature. And for me, it's a direct property of nature. To me, mass is more fundamental. But one physicist went so far as to say that momentum is the reason that an object travels from one point to another. For him, it helped. For me, it doesn't help. So we can write this as PA initial plus P initial plus PB initial is equal to PA final plus PB final. Or obviously, since I'm adding up, this is with a two-particle system, we can expand that into however many particles you want. The sum of P x initial is going to be equal to, these are vectors, dx final. So if I have an n-particle system, it's just a matter of, you add up all the momentums beforehand, all the momentums afterwards, it should be equal. And then physics textbooks, and it's not easy to convey on the board just because of the nature of the way we make our P's, but P initial equals P final. This is indicating total. The capital letter typically means total momentum, and the smaller lowercase p means we're talking individual. My capital P's and lowercase p's are just difference in size. Here, I took out some of the serifs, but my p's look the same, so I'm not going to really deal with that distinction a whole lot. But this is the mathematical formulation or representation of conservation of momentum. All right. Questions here before I contradict myself? They let the contradicting begin. So I have a particle right here, or I have a marker right here. Let's assume it's at rest. What is its momentum?
0.
Okay, in whatever the appropriate units are. I let go of it. It suddenly started increasing in speed. Was the momentum of it still 0 as it fell? As the object falls, is the momentum 0? No. So, but I just said momentum is conserved, yet there's an example right there of momentum not being conserved. Or was it? So, introducing the concept of a closed system and an open system. In a closed system, I'm taking into account all of the objects that possibly have an influence. So in the case of the marker falling, the closed system, well, what was pulling it down?
Gravity.
From.
The Earth.
So in a closed system, I would take the marker and the Earth both into account. If I look at just the marker, it has a force acting on it from outside the marker. It's not exerting a force on itself. And so that would be an open system. So in an open system, I've got outside influences. So external force applied to the system. And in a closed system, the external force is 0. It's slightly different wording. In a closed system, I'm taking into account all the objects involved. In an open system, I'm not. So if I'm an open system, is there some way of actually predicting what the change in momentum is? Well, yes. Because if you'll notice over here, I started out with force times time, and I hadn't done any switching across the equal sign up to this point. Well, this is just the change in momentum of A. So this, force times time, is equal to the change in momentum. Or we can make it a little fancier. F dot dt is equal to the change in momentum. Absolutely horrible delta. That's just a multiplication dot there. That dot probably won't get rid of it. So this force times time, if force is constant, so if force is constant with respect to time, this is just equal to F delta T. This has a special name other than change in momentum. And here's my most obscure clue. Well, perhaps tied with the Bobby Sherman clue. From a commercial in the 70s, if someone suddenly buys you flowers, that is called it's like you don't watch 70s perfume commercials. Impulse. And so with energy, we've got a work-energy relationship. In momentum, we've got an impulse-momentum relationship. There's only one, though. Before I erase anything, any questions? Okay, let's do it. Let's use some stuff. All right, so if I've got, I'm gonna deal with a closed system. We'll make this a 3 kilogram mass heading to the right. And over here, I've got a 4 kilogram mass heading to the left. Let's say this was going 6 meters per second, and this is going 2 meters per second. They collide and stick to each other. This is known as a perfectly perfectly inelastic collision, which I will sometimes just abbreviate PIC. My naming conventions are going to potentially be different than the books, just because I've run across 2 different naming conventions, and instead of trying to remember which each book does, I came up with a 3rd one that is less ambivalent. I'm not sure that's the word I wanted. Ambiguous, that's the word I wanted. All right, so as a general rule of thumb, when you're solving these problems, you hear collision, or you read collision, or something, a variation of that word, you should be thinking conservation of momentum. If 2 things are smacking into each other, think about momentum being conserved. So we need to figure out what is the total momentum beforehand. So I'm gonna have my 3 kilogram mass here initially, and my 4 kilogram mass initially. I will do subscripts based upon the masses. If you wish to do different, that's fine. What is the initial momentum of the 3 kilogram mass? A little reminder over here. What?
Kilogram meters per second.
Yeah, they did not come up with a single word for it. But since, if we look over here, since impulse is the same as the change in momentum, the units of momentum must be the same as the units of this. So that's also a Newton second. Newton second. What assumption did Benjamin make? He's affected the rest of how we solve this problem. Because he is powerful and mighty. What did you do? So powerful and mighty, you didn't even notice what you did. Well, let's do the second one and see if that'll jar something. All right, what is the momentum of the second one?
8 kilograms per meter squared, or
Newton seconds.
meters.
There is a mistake on the board now. Because of what Benjamin did to start with.
Something along the lines of. How to word it. With the 3 kilogram box, no other forces are acting on
Yeah, there's no other forces acting on it. We don't have to worry about that. It is a closed system.
it. Okay.
So there are only 2 objects in this universe.
Oh, direction.
Yes.
Yeah.
Momentum is a vector. As soon as he said 18 kilogram meters per second, he established to the right was positive. Therefore,
Negative 8.
yeah, negative. What is the total initial momentum? And it's as simple as you think.
10 Newton seconds.
You kilogram meter per second?
Yes.
Is that what you said?
I said Newton seconds.
Newton second, okay. All right, so we have 10 Newton seconds as the total initial momentum. What's the total final momentum after they collide and stick together?
It should be the same.
Yes, it should be, and it is. I've asked that on tests. Conservation momentum is a rather fundamental conservation law. We had them solve for the initial momentum, then said, what's the final momentum? Too many people missed it. All right, so afterwards, since they stick together, I know that the final momentum is mass times velocity. V final. It's mass final times velocity final. What's my final mass?
No, should be the same,
Okay.
which is. Was this for any particular one?
All right, given the way that you're talking about it,
I mean,
MA final. V final plus M, vector over the wrong one. MB final, V final. Why do I have only final, the F subscript here for the velocity?
well, we're worried about final momentum. So we wouldn't want to be,
There's something special about this case which allows me to just do V final.
they stick to each other.
Yeah.
Oh.
If they're stuck together, they will be going the same velocity afterwards. All right, so this becomes 3V. I'm just going to simplify the notation. Plus 4V, 7V. Is equal to 10. So the final velocity, 10/7 meters per second. So what I had done the first time I wrote it up there is, before you asked, are we talking about which one specifically? Since they are joined together, I was treating them as one object. In essence, this, except you factor out the VF and you're left with MAF plus NDF, which would be 7. All right, questions to hear before I ask them auxiliary questions on the same problem?